Thank you. Well, thank you so much for that gracious welcome, and that was a fantastic meal. Would you not agree? Absolutely. And I've had the privilege of speaking at a number of ASQ chapters across the Midwest, and you have an exceptional chapter, something very special. So congratulations to the leadership and also all the members. This is a really, really nice gathering. I have on the table here a copy of this presentation. If you find this interesting and helpful and you would like to take a copy of this presentation with you, by all means, pick up a copy. I also have some sheets of paper. If you would like to make contact with me, just leave me your contact information. I'll be happy to get back with you. If you have any questions or comments regarding the presentation, please provide that feedback. We do have forms, just a sheet of paper. If you have a case history you would like to share tonight and maybe get my feedback or input, or if you have an analytical lab in which you've pursued root cause and you think it would be beneficial to the group to hear about, please write that down on a piece of paper. Jaron Lance Robbins, he's raised his hand over there. He is your go-to guy tonight. If you need anything related to my presentation, need more forms, he's the guy to talk to, okay? All right, here's my contact information. If you ever have any questions, feel free to get a hold of me. Let's start off with a little bit of history. Everything, all my literature says Excellus. Well, what's an Excellus? Well, it's a made-up word. You know, it's easy to copyright, and you know how branding is these days. If you can make up a word, that's a great thing. But where did we come from? Well, here's where we came from. Excellus is what we're branded as today, but really our Fort Wayne Excellus presence really traces its roots back to Philo Farnsworth, the inventor of TV. Isn't that interesting? So he was purchased by ITT back in the day, and then ITT went through a number of transformations, splits, corporate splits, this and that, and eventually ITT Industries spun off and split into three different entities known as ITT, Xylem, which is the water treatment, water handling, and then Excellus. So Excellus is a pure play defense contractor at this point in time. And these are the different Excellus divisions. We're into night vision and communication systems. This is the division that owns my lab. And then we have electronic systems division, geospatial systems division, all the weather satellite imaging that you see on the Weather Channel and just on the internet when you're looking for weather information. That imaging comes from our imaging systems that are deployed in space, information systems and mission systems. So at one time, our lab served not only all these defense divisions, but the other ITT divisions, such as leisure marine and things like that. So in my career in failure analysis, I've seen everything from boat bilge pump control systems to advanced satellite imaging systems. So truly, our lab has served virtually all the commercial industries that you can think of. All right, so let's move on. And then within Fort Wayne, there's a number of engineering services that we're involved with, including electronic assembly, EMI Tempest testing, printed circuit board design, metal fab, and failure analysis. So we are located in Fort Wayne, just 2 hours away. And there's a picture of our facility. Let's get on into the case histories. And before we go into case histories, different failure analysis labs have different focuses. Some are focused strictly on mechanical materials failure analysis. Other failure analysis laboratories focus on electronic components. Some analytical laboratories are even more specialized. They might be water testing, they might be material composition testing. They can, a lab can be as focused or as broad as they want to be, and especially many captive labs are very, very specialized. They're specialized to focus on the product that their parent company produces. Well, since the reason I gave you the background of ITT and Axcelis, that helps, gives you a better appreciation for the diverse products that we had to analyze and get involved with. And for that reason, our lab is really set up to do both electronic component and mechanical failure analysis and materials analysis. And we've performed well over 20,000 analyses in our history, very much steeped in both electronics and materials and mechanical failure analysis, and a lot of different areas of expertise. Our areas of expertise actually bore into and delve into many industrial processes that are the building blocks for the components and assemblies that we integrate into very complex systems. So it's amazing how many phone calls show up at my desk related to metals finishing or heat treating, things like that. I mean, these are fundamental industrial processes, but yet we have systems engineers calling the lab guy to understand the details of these processes. Why? Because many times the failure analysis fault tree, if you will, the presentation we had earlier during our dinner meeting, the 15-minute presentation on the Challenger disaster, it showed how this system failure really was the result of a very, really a combination of things, right? A well-intentioned over-testing of an O-ring combined with some political pressures to launch, combined with perhaps some environmental issues, perhaps, you know, a little bit cold that day. So a lot of these things combine to that. And here are a few of the instrumentations that we have within the lab. We have micro FTIR, real-time microfocus X-ray, scanning acoustic microscopy, scanning electron microscopy, force testing at the micro level and the macro level, and photo emission and infrared microscopy. Lots of optical microscope inspection. And I go over this list to give you appreciation for the types of tools that are required for failure analysis of a broad range of components and materials. So when family asks me, well, what do you do for a living? You know, explain, you know, and the first thing that comes to my mouth, out of my mouth is failure analysis. And they say, you're a failure. Well, I've made my living. I've lived my living with, you know, making money off of failures. Sad but true. But it has been a very rewarding career. You know, as you watch the failure analysis of the Challenger disaster, I mean, really, that effort, that failure analysis, think of what it accomplished. It really conclusively identified the root cause of failure and what is the benefit to mankind by getting to root cause. You can imagine. You can prevent the next disaster, loss of life and property, right? I mean, that's a very noble effort. But before I pat my profession on the back too much, it's it has been a very rewarding career, and I'm excited to tell you more about the discipline, and hopefully it's a help to you. Okay. Now, for the managers in the group, we have to sell them on the business case for why we do failure analysis, because the managers in our group will always be suspicious of the engineers. It's like, why do you want to go and spend my budget just for this interesting lab exercise? Why would you do that? And of course, you have to have a good value proposition, right? What benefit is it from a business perspective? So this is for all the managers out there. And first of all, this is why we do what we do in general. all of our professions, all of the businesses that we work for. Why do we do what we do? And it's because whenever something is difficult to do and important to the customer, this presents an opportunity for competitive advantage. So the companies we work for are, I would say probably in every case here, they're the best or one of the best in the industry. And what we do is not easy to do, because if it were easy, everybody would be doing it. So when you are able to quickly and conclusively drive to root cause, my proposal is that gives you a competitive advantage versus your competitors who may make multiple attempts at driving to root cause, and that creates a problem. So the governing principles in a marketplace as it applies to root cause investigation is prompt and effective problem resolution is important to our customers. Does anybody have a customer here who doesn't care if you ever solve the problem? So there's no hands going up. I didn't anticipate hands going up. Now the likelihood of effective problem resolution is high with a good understanding of the problem, also the physics of failure. So we have to understand the root cause of physics of failure. And for the average company, the physics of failure are difficult to conclusively determine, especially in a timely manner. And so when you've had a very highly visible failure, whether that is a first article test failure, whether that is a field failure, these things can be very embarrassing, and they can jeopardize our relationship with the customer. And then the next bullet is inconclusive root cause determination leads to guesswork corrective action, and ineffective corrective action results in repeated failure and customer dissatisfaction. So most of us have customers that can put up with a failure because, you know, it's not uncommon in industry to have problems. And the more complex our systems, the more complex our product, the more risk there is to both the producer and the consumer. But when we say we've solved the problem, when we say we've identified the root cause, and we really haven't, that's what really gets us into trouble with our customer. That's what really tarnishes our reputations as suppliers and manufacturers. And so the last bullet is kind of self-serving, but this is how our laboratory has survived in a very challenging economic environment by basically quickly and conclusively driving the root cause. Why? So then you can very effectively implement corrective action and then move beyond the failure and then restore your reputation with the customer. So that's a value proposition, that's a business strategy. So let's get into the fun stuff, okay? So what I'm going to show you are some actual case histories. Now these have all been sanitized and, you know, to protect the innocent. The names have been changed. But what I'm going to show you, these are heavy on the, I would say, the electronic side of the technology spectrum. And what I would encourage you to be thinking in the back of your mind that there are many mechanical and material science related failures that we see. Some of those are analyzed for outside customers because we're a lab for hire and we do quite a bit of work for diverse industries. And so I do not show those examples here. So these are homegrown problems, if you will. All right, so this was a hermetic. This is the case history that involves a hermetic DC to DC converter package. So think of a metal box with leads sticking out of it to make contact with electrically with the outside world. And there is an inert atmosphere sealed into this case, this can, if you will. And in this can, this DC to DC converter failed. And actually there were two, this was kind of a rare bird, and it's very rare to have two causes of failure in a single failure. But in this case, this is almost like a system within a can, if you will. There's a lot of components within this hybrid. And we had two things going on. We had a disbonded underside lid tape that drooped and adhered to internal bond wires. What are bond wires? Bond wires are little metal wires that make contact from one point of the circuit to another. So those of you who aren't in the electronics industry, just think of an uninsulated wire that goes from one place in the circuit to another, and there is a piece of adhesive tape that normally should stick to the underside of the lid. It can have multiple functions, including being a particle getter. So so any incidental particles that are left inside of this thing during manufacture would rattle around and stick to that adhesive tape. Okay, but it disbonded, drooped down, and made contact with bond wires, and then they would pull up and cause an open. There was also a shorted transformer, and I'll get to that last, but along the way we saw tin whiskers. How many of you are familiar with tin whiskers? Absolutely. That is the nightmare for high reliability electronics. And now this was not a cause of failure, but it was just kind of a bonus, if you will. You know, that's a sick mind for you when you think of tin whiskers as a bonus. But we found those growing off of a pure tin-plated inductor standoff. And that was a standoff that was common within this assembly, used on two different inductors and two transformers. The whiskers had grown to a length that really wasn't a risk at that point because of the geometry, the spacing between between elements within that circuit. But chances are those whiskers were not done growing, and over time they could have become more of a risk. So this is something you do not want to see. And these are metal filaments that are extruding out of that pure tin-plated surface. So it's a phenomenon that's very, very interesting, and probably I shouldn't go into depth on at this level. But the shorted transformer is depicted down in these last two images. And this is a transformer that's been cross-sectioned, okay? And this white circle shows you the area of interest that's then magnified over in the bottom right image. And these two adjacent windings are electrically shorted. Now, magnet wire has a insulation, a thin insulation that protects the wires from shorting against each other. But in this case, these adjacent windings were shorted, and that was the cause of this module failure. Well, just as the Challenger video demonstrated, you have to keep asking why. Okay, so why did the module fail? The module failed because there was a shorted transformer. Why was there a shorted transformer? Well, the transformer was shorted because adjacent windings were shorted. Why were the adjacent windings shorted? Well, it turns out this did not take less than I would say a week to determine, because this involved research on a number of materials. There is a potting material that's used to bond the transformer to the standoff. That potting material was incompatible with the magnet wire insulation. So essentially softened, dissolved, affected the physical properties of that wire insulation. And so unbeknownst to the manufacturer of this module, they had used an incompatible material. So that was the next why. And then, of course, if you were to be really thorough, why did they choose that material? Well, it was not well published that this type of magnet wire insulation would be incompatible with that staking. So it turned out that there was not a blatant engineering malpractice involved. So with that information, corrective action could then be implemented on the next build of that module. So root cause driving corrective action, that's how we bring value. Any questions on this case history? Okay. Okay, case history number 2, and this is a flex circuit failure. What's a flex circuit? Everybody's heard of printed circuit boards. You open your computer at home, you see circuit boards galore inside. Okay, most of those are rigid circuit boards. Now there are flexible circuit boards as well. In this particular case history involves a flexible circuit. And during troubleshooting of the circuit that contained this flexible circuit, the troubleshooters, the engineers, the technicians identified a node, and node's just a fancy word for a particular point on a circuit where there was a likely electrical open. So it should have been electrically continuous, but it was electrically open or intermittent. And so that allowed us to focus our analysis on that particular plated through hole. And so what you have here, let me give you a description of the anatomy of this feature. Okay, you have, this is 1/2 of a plated through hole. This is plated copper that's plated onto a drilled hole within the flex circuit. These smaller lines here are layers of copper that go elsewhere in the circuit and make contact and provide signals in power and ground elsewhere in the circuit. This is what's referred to as a T-joint. Okay, so this trace, copper trace, should be electrically continuous with this barrel. And all this should be tied together and where you can get signals from one layer to another, or power from one layer to another. And you see this narrow demarcation. There should be no line here. That should be all continuous copper. And you can see this trace is a little bit healthier, but overall, this plated through hole has problems. It's an unhealthy one. In a healthy plated through hole, this should all be continuous. Okay, and so, all right, if you start down the list of why did the circuit fail? Well, this via plated through hole had electrically open T-joints. Why did the why were the T-joints open? Well, that's where we really had to earn our money. We performed an extraction. We cross-sectioned that plated through hole about up to the 50% point, and then we extracted it out of the circuit. So behind these traces would be kind of a mixture of Kapton, different polymeric materials. And we essentially pried that half circle out of that circuit and then analyzed the surface. So these features here line up with the T-joint, okay? And so you're seeing this dark material is actually an organic material on the surface at the T-joint interface. Ought not be. That ought to be a good metallurgical bond, and so that you have good electrical continuity. Okay, so the flex circuit failed due to an open plated through hole, due to T-joint problem, and the T-joint problem was related to organic material within the T-joint. And so without disclosing too much information, supplier information, we ended up conversing with the supplier of this flex circuit and found out their bill of materials, all the chemicals and materials used in the manufacture of this flex circuit. And by doing an infrared FTIR analysis, which stands for Fourier transform infrared spectroscopy, we identified that material and traced it to a material used in their process, which gave us insight into which step in their fabrication process caused that problem. So ultimately, we traced it down to a step in the problem, or a step in the process. Okay. Any questions on this? Great. Okay. All right. Okay, this is getting a bit more into material science, but material science within the electronics realm. So we have a potted electronic assembly, and again, this presentation has been sanitized, so there's a lot more detail behind that very concealed description here. But imagine you have a potted assembly where you have epoxy as a potting compound, and you have electronic devices. We have a surface mount device, an IC, that has gold-plated leads soldered to a circuit board. So this is a mini circuit board within a potted assembly. This is a solder joint, and this is a gold-plated lead going up to an integrated circuit. So the manufacturer of the integrated circuit had a gold-plated finish on his leads. And they soldered, the manufacturer of the potted assembly soldered that component to the circuit board. And we saw fractures in the solder joint. So these horizontal lines are fractures within the solder joint, and that was a real concern. Now, as I allude to in this text box, we saw no evidence of pre-tinning prior to soldering. So pre-tinning is a term we use in the electronics industry for wicking away an unwanted metal by dipping the component leads in a material of choice, usually a tin lead solder or some other solder material. And when you do that, the gold is highly soluble in the molten solder, and you end up wicking that away during that tinning process. And by doing so, you eliminate or reduce the risk for a gold embrittlement. So gold embrittlement is a failure mechanism at play in these solder joint failures. Okay, now we're going to show you a little bit of metallurgy here. Going down to this lower right-hand image, this is a cross-section of the lead going into the solder joint. This bottom layer here is the pad on a printed circuit board. Okay, and then the light material is the solder joint. And then we have a higher mag image of this area of interest. And now you can see a fracture path following the surface of the lead. And if we went into even higher magnification, what you would see gold tin intermetallic crystals preferentially following that gold-plated lead. And so those gold tin intermetallic crystals behave much differently than the bulk solder. They're mechanically inferior to bulk solder. They don't give, they don't creep, they're brittle. So if you have a lot of force applied or shock, they'll behave in a more brittle manner versus tin lead solder that we love in the defense industry because its properties are well known. It'll creep, it'll give with thermal cycling. Okay, so we were able to determine the root cause of failure not just by this image. This was a clue. This was a visual cue that, oops, it looks like somebody forgot to do a very important step. So in a high reliability program, it is standard to do a pre-tin on a gold-plated device to avoid gold embrittlement. And when we did the cross-sectioning depicted down here, we confirmed that gold embrittlement was at play. And of course, I have to give you a bonus. So the bonus failure mechanism was that there was an inductor magnet wire that broke, and that was actually the cause of failure in this potted device. So the gold embrittlement was kind of a latent failure waiting to happen, but there was still electrical continuity in all these peaks and valleys of this fracture surface within the gold embrittled joint. So this magnet wire failed during test, most likely due to lack of strain relief within that assembly. You can see it fractured as it enters into a solder joint, probably at the point of greatest stress concentration. So just as we would expect. And if they would have put more of a strain relief in that magnet wire as it approached, most likely it would have survived. Any questions on this? Yes?
On all these failures, then you have the task beyond identifying the failure. You can see how you can improve the manufacturing process, but if you have a number of components out in the field with potentially these characteristics, then you have to somehow bracket it and decide what your remediation is going to be for things that are already in use. Right?
You're exactly right. So data from this analysis will help you in many ways. First of all, what is my risk, okay? And how do I contain this? For instance, knowing the failure mechanisms, I could then go into the population and perhaps X-ray a bunch of these and look for the fractured magnet wire. I could then maybe have taken a sample of those, maybe looked at different date codes, taken a small sample of each date code, and cross-section those, depotted cross-section them and say, hey, did they or did they not pre-tin these leads? So then that gives me an understanding of the risk, and from that you can make containment questions, or you can make containment decisions. What's the risk to the customer? Do I need to recall product, or is the risk contained within my facility? I found all the bad ones, you know. And then, there's a number of decisions, and then the corrective action. Sir, just as you indicated, how do I correct this going forward? Well, I am going to pre-tin my gold-plated leads. I'm going to put more strain relief in this magnet wire as it approaches, you know, a fixed point here, and that'll give me a more robust design. Thank you. Great point. Now this is a very interesting one. This is a multi-layer chip capacitor. And so this gives you some materials analysis. See, I'm trying to convince you that all these electronic failures are really materials analysis. So I'm trying to please everybody here. But so you have a mix of materials and different material properties. You know, a multi-layer chip capacitor is really, it's a composite. You know, you have a brittle material, that being the ceramic dielectric material. And then you have silver metallization for the plates, the interdigitated plates in the chip capacitor. And then the end cap metallization can be a multiple metal types, usually a barrier metal. You'll have a metal that's fired into the ceramic, a barrier metal, and then a final precious metal final finish. But the history here is that a chip capacitor that was in a larger assembly shorted out during a circuit level test. And this was on a program in which every failure would be scrutinized in detail. The customer had a lot of visibility in here. It went into a system that really needed to be a high reliability system. And so when we identified a fracture that traversed multiple interdigitated anode-cathode plates, that told us that we pretty much had identified the mechanism. That told us right away that, hey, the chip cap had fractured. That fracture path provided then an opportunity, a path for electromigration. So this SEM image down here, scanning electron microscope image, is a fracture path that's going diagonally from one plate in the cap to the other. And those adjacent plates are of different potentials. Okay, one's going to be at a positive, one's going to be at a negative. When you have a positive, when you have a DC potential, that gives you an opportunity for electromigration along that path within that dielectric. And now this image over here is just, it's a picture of a wall in our lab. And so what we did is we pinned up a number of high magnification SEM images showing how the fracture traverses from one layer, one plate to another plate to another plate to another plate. And in most of this fracture path, you can see silver metallization migrating along that path. That migration of silver metallization along that fracture path is what caused the electrical short. So then, okay, you keep asking why. Well, why was it shorted? Well, we had a fractured capacitor that provided ample opportunistic fracture path for electromigration. Well, why was it fractured? Ultimately, we did find an issue with stock capacitors from the supplier, and that turned into a very large screening process where we screened a lot of stock capacitors before they were ever put into products. So it was a high reliability program. The customer could assume no risk or little risk, so we mitigated risk by looking at and scrutinizing everything before it got put in product. Any questions on this case history? Wow, you guys are so polite. before I go on, I'll show you just a counterfeit component example, because what failure analysis lab would be complete without some component, counterfeit component detection capability. But before I move on, I want to give any of you an opportunity to mention a failure. I can give you some free advice or some free speculation here. My goodness. Well, that's fine. We don't have to have anybody air their dirty laundry tonight. Okay, what are counterfeit components and why are they an issue? You know all those scrap electronic things you turn into the county? On Amnesty Day, your monitors, your PCs and all that. You ever wonder where those go? Well, a lot of them are, some of them are, they're reclaimed, they're packed into container ships, and then off they go to the four ends of the earth. There are developing countries where there are entire villages or communities that basically go through scrap electronics and reclaim components and precious metals and things like that. And these are, in some cases, very destitute people, and this is their only means of survival. And unfortunately, there are influences and people in the world who exploit those workers and take the reclaimed components and then remark them, resurface them, remark them, and then present them as new product or as product or components that have been essentially, they represent those as essentially new product. Now, the most vulnerable companies for buying counterfeit components would be those companies that have legacy programs where they can no longer find that component manufactured new by the original component manufacturer or the authorized distributor. That component ceased being produced, ceased being sold years ago, but yet you have this old legacy program that requires the use of that component. Where on earth do I find that part? My customer just ordered 10 replacement units. Where do I? So now I have this demand for the mill materials that I haven't purchased in years. Well, your faithful supply chain friends will then go off and consult brokers, non-authorized distributors, and say, hey, can you find me this old technology component? And they go off and they search, and the brokers will find a source and come back to you and say, I think I've found what you need. Do you want to buy them? Well, sure, I'll buy them. Many times, sometimes, these brokered components are in fact counterfeit components. Not always, but sometimes. Often enough to cause us, especially in the defense industry, real headaches. It's become such a problem that Congress and Department of Defense passed a law that says all defense contractors are accountable and responsible and financially liable if counterfeit components make their way into finished product and delivered goods. So even if you unknowingly incorporate counterfeit components, you think that's a genuine article, you have a CFC that says, hey, this is a new part, it's authentic, you put it into your system and it fails, or somehow later on you find out that, oh, that really wasn't authentic, that defense contractor is responsible for making it right. And so there's a lot of risk. Okay. So I'm just going to show you an example of a counterfeit part, and one of the several of the ways in which counterfeiters represent or are able to pass off a counterfeit as new is they remark the parts. They grind off the original markings, which may have an old date code, okay, or maybe it's a lesser part, and you are looking for an upscreen part, or you're looking for a faster part or a slower part, they can grind off the original markings and apply a black coating known as blacktop, and then apply new markings. And then sometimes they replate the leads to substitute a leaded finish for a Rojas finish. So that's a real issue too. Those of us in the defense industry, we do not especially appreciate lead-free finishes, because why? Pure tin is a real problem for us from a reliability risk, so we prefer leaded finish. Sometimes a counterfeiter will take a dummy part, it looks like a part, but there's no active component inside. It's just the package. Okay, and again, common target for counterfeiters, hard to get, legacy components. Okay, so there's a number of standard things we do, including just good microscopic inspection. A good trained inspector can detect a lot of things. X-ray inspection, if you have a known authentic part, you can compare that known authentic part to the unproven part, the suspect part. You can do electrical testing, curve tracing, DC parameters. You can do XRF, verifying lead finish, X-ray fluorescence testing. You can do resistance to solvents. Okay, that blacktop material I described earlier. Some of the less sophisticated counterfeiters can apply a blacktop that is soluble in certain solvents. The more sophisticated counterfeiters are using materials that are very difficult to detect. And then finally, internal inspection, especially with integrated circuits. Many times we'll decap or look inside a part, look at the die markings, and verify that the die markings are consistent with a known genuine part. So it's always helpful to have a known authentic part to compare to. So we have some advanced methods for detection of counterfeit parts, and this is where I would caution any of you who are in an industry where you have to do some discernment, where you have to practice discernment and decide, is this authentic or is it not? There are counterfeit detection labs out there that have minimal capability and may, even with best intentions, miss a counterfeit part. So this is where we implement some of the more advanced methods, including scanning acoustic microscopy. We do use energy dispersive spectroscopy when XRF is inconclusive. We can perform scanning electron microscopy as kind of a backup for verifying the presence or absence of blacktop. And FTIR will capture a fingerprint of the surface material. You can compare that against the bulk material of the package. And functional testing. You can spend as much money or as little money on functional testing as you want. It can get very expensive, especially if you have a part where there's really little to no support in terms of having a functional test. So here's a case history where we had a mature program facing component obsolescence, and the parts were not available through the original component manufacturer or the authorized distributor. We purchased them through a broker, okay? And the test engineers found that they could make these broker purchased parts work only if they changed several adjacent component values, okay, in the circuit. So that's what prompted the engineers to come to us and say, you know, what gives here? And we looked into it further, and we found die paddle delamination. This is where we're using the scanning acoustic microscope to look inside. This delamination can happen very easily with when you take parts off of a reclaimed board. But when we looked further and did a surface wave acoustic imaging technique, we were able to see grinding marks underneath the blacktop coating. And you can see a little bit of ghosting of prior markings. So this is where a good optical microscope can really come in handy. But here's the thing. We thought we were purchasing TI parts because the package was marked with a TI logo, right? But the die inside was marked with Micrel. So that's the case where a Micrel part was reclaimed probably. They ground off the original markings, put blacktop down, and then applied the new markings. So that's a good case history for you. That's a true-to-life issue. Here's a side view of an integrated circuit that has had blacktop coating applied. See how that sheen is different than the bulk material? And we applied a solvent to one half of the part, and you can see when we removed the blacktop, you have grinding marks. So that would have failed permanency. With the few minutes that I have, I'd like to go through a few more images. If any of these capture your eye, I can give you a little bit more detail, but I promise not to run over on time. You know, this is kind of just a whirlwind tour of our life in the lab. This is a cross-section of a electrolytic capacitor. That's a tantalum capacitor. That's a tantalum slug. This is a lead that is attached and goes out to the outside world. So this is one lead, this is the other lead, and the problem was related to the attach of this lead. This is a precision resistor, and this is the resistive element that's printed on top of the resistor. The protective cover lay has been removed to look inside. This is just a part of a cable harness that's terminated at a connector. Now you'll notice that this terminal crimp is different than this. This is a terminal workmanship issue where this lack of crimp could result in a lack of reliability down the road. You get into a dynamic environment, a lot of vibration down the road stuff, and this could fail prematurely. This is a picture of a circuit board pad that's been printed with solder paste before reflow. So these are tiny, tiny spheres of solder paste under high magnification. This is our friend the multi-layer chip capacitor cross-section. This is a ball grid array device soldered to a circuit board. And so this is the solder ball that's fully reflowed and collapsed. And you can see you have a variety of metals represented here, including barrier metals, the solder, and the copper traces on both the device and the board. This is photo emission microscopy, where we're looking, the purpose of this tool is to look for a fault site on an integrated circuit. And we have an out-of-family emission site on this input protection structure. That's the bond wire that goes out to the outside world. This is an input protection structure that could be an ESD protection structure, polarity, wrong polarity protection, what have you. And this blue dot, collection of blue dots, represents this circled area shown in the optical. This is an optical microscope image. Make a long story short, this corresponds with an electrical overstress damage site that we proved existed with this photo emission microscopy. Turned out to be a test set issue, wafer level test. The test set had multiple power supplies that had to power up in a certain sequence. If they didn't power up in the correct sequence, they could cause an electrical overstress, and that's what happened here. Here we have, this is a flex circuit, portion of a flex circuit, and we used infrared imaging to show a resistive short. So this is giving off an IR signature because there's a resistive short. It's giving off a little, I don't know how many milliwatts, but that helped us trace it down, the location of this resistive short, to a particular physical location in the assembly. And then we were able to do further analysis from there. This is a tunable potentiometer, and we're able to see the inner workings. This is a tuning screw. What you can't see is there's, okay, now this is the wiper that the tuning screw drives, and that drives the location of that wiper around to help position it on the printed resist element on the potentiometer. And that's what gives you your different resistance values. And so this is a top-down view in the X-ray. So there's a tuning screw, there's the fingers of the wiper, and there's the resistive element printed on the ceramic. Isn't it kind of fun to see the inner workings of things? Now this looks like a chia pet, but what that actually is that is a silver-plated terminal. It looked dirty, and the inspector brought it to us and says, hey, this spaceflight terminal is dirty. What is that? We put in the scanning electron microscope, and we found these little filaments growing out of the surface. We analyzed those using energy dispersive spectroscopy, and we, based on the elemental composition, we determined that it was most likely the result of plating salts, not thoroughly rinsed, left behind on the plated surface, and the presence of those salts and residual stress in the deposit causing this crystal growth to occur. So, and these are some acoustic images showing, in this case, fractures in a power transistor beryllium oxide substrate. And this is a IC that has gone through popcorning. What is popcorning? That's where the plastic package on an IC delaminates from the silicon die, and you end up with pulled up bond wires. It can be really catastrophic in its effects. But this red area is area of delamination, so scanning acoustic microscopy can be used to image a solid object, what ought to be a solid object, and detect voids and delamination and cracks and things like that. Okay, that's an X-ray of an RF connector connection. You can see it's not completely engaged, male and female. Here's a cross-section of the same item, and you can see we have very good fidelity, both in cross-section and an X-ray. It's a close-up of metallization on an integrated circuit, and there is a failed bond wire, or a bond wire getting ready to fail. It's about 75% fractured, and that's a stranded wire bundle down the bottom right hand, and stranded wire bundle that just failed due to tensile overload. And our friend the circuit board, play-through hole, there's a circumferential void created during the circuit board fabrication process. Chemicals got into an area that should not have been exposed to the chemicals, ended up etching away the copper, and an open resulted. And here's another type of circuit board defect where you can see a void in the plated copper. Poor quality. You can now in cross section see that same area. Okay. There's a IC die. Here's a relay. Lots of good stuff there. Okay, this is my last example, and I'll quit for the evening. Take on any questions if you have. This is an FTIR spectrum of residue contamination found on a electrical switch. That brown material was analyzed, FTIR, came up, the unknown residue is in red. We searched against our library of spectra. Best match was high fructose corn syrup. Well, everything's made out of high fructose corn syrup, you know, especially my daughter, you know. Okay, so I was having a good day that day, and I asked the engineers, I said, go to the break room, gather as many brands of pop as you can, let's evaporate the soda water, let's look at the syrup, and let's see if we get a match. And I was on it. I'll claim full credit, it was my idea. And we got oh man, it was a terrific match with Pepsi. So our unknown is in red, Pepsi's in blue. This is a fingerprint region of the infrared spectrum. And what's important is that the peaks coincide with each other, known and unknown, in the time domain or wavelength domain. So that's what's important on that. I have this presentation and a few more goodies on the CD. Avail yourself of that. I'll stick around for a few more questions, but thank you so much. Yes?
It seems like your are really good at identifying what failed, but the real secret to getting to root cause is your understanding of your manufacturing process and the use cases. Would you comment?
Yeah, I agree. So you know, failure analysis many times is reactive. How can you be proactive? How can you design a process and so that you don't have these failures? And how can the lab be involved in that? Is that kind of where you're going? Yes, I failed to mention that one of the uses for our lab is to evaluate new processes, okay, and look at the key characteristics, the critical characteristics of those processes before they're qualified and approved, and to look at almost doing a PFEMA, if you will, and in that PFEMA, what could go wrong, and what will you look for, and so we do a lot of process development support. Is that close? Thank you. Any other questions? Yes.
You showed a couple of interesting examples of solder joint failures, like tin whiskers and the structures. Do you have any other examples kind of showing distinct difference between tin lead and lead-free solder, coming from failure analysis perspective, where you see that tin lead is showing something better or worse than something else?
Great question from our reliability physics professor back there, and the answer is our lab has gotten involved with life testing of both lead-free, or excuse me, non-leaded solders and traditional leaded solders, and there is a difference in performance, and there's a difference in reliability, and understanding the characteristics. The lead-free solders just behave differently. They have different mechanical properties. They don't creep as much, and so what we've seen is that they've performed very well in certain solder joint designs, and other solder joint designs not as well. So it's kind of a depends type answer, and so there's a reason why leaded solders are the tried and true in defense electronics. Their properties are well known and all that. So the quick answer to your question is our lab gets involved with root cause analysis of solder joint failures, and we look for things such as fatigue, such as gold embrittlement, such as black pad. There's a lot of defects and failure mechanisms associated with solder joints, a lot of metallurgy involved, and we've done the forensics that are the output, that are the outcome of life tests, where you try these different processes, you try these different metallurgies in your electronic assemblies, push them to the max until you get failure, and then you ask yourself, what is the failure mechanism at play, and that's where we come in. There's not a short answer to your question, but typically we see the failures occurring in components and terminations where there's the highest amount of stress, which doesn't surprise you, I'm sure. And there are ways to mitigate that with certain manufacturing processes. For instance, on a ball grid array device or a flip chip device where you have solder spheres, the corner sphere is going to typically have the highest stress. So you design around that by not having any critical signals going to that corner ball. Usually that corner ball will be a redundant signal or redundant power or ground, where you have that covered in multiple locations within a device. And then you can also incorporate manufacturing aids, which probably go beyond this forum. We can talk after this meeting. I can tell you some details on that. Was there another question over here? Yes.
To what degree do you participate in the GUIDED program, particularly for counterfeit components?
Right. We provide the raw material for the GUIDED. In other words, we provide a very thorough analysis report saying yes or no, these components are authentic or they're counterfeit. And this is why we believe they're counterfeit. At that point, supply chain works with the legal department, to fully comply with federal regulations, because federal law requires you to report when you find counterfeit components. And so we're, as lab guys, we're just so happy to just throw it, to give those results over to legal and supply chain. Say adios. But good question. As it should be. You know, we have to catch the bad guys. And many times the counterfeiters are using those resources, the money they get from counterfeiting, to fund terrorism, organized crime, really, really bad things. So we want to get the bad guys. Any other questions? You've been terrific. Again, my business card is on the table. Call me with any questions or concerns. Thank you, Elizabeth, for hosting me again, and you've all been so gracious. Thank you very much.
Thank you, Nick. Hope we appreciate you coming, and I'm sure some